Hello and welcome back. As promised, right back on the Verbose Code by Tux here at Dev2 Next in Colorado Springs. And my next guest is Barry. Welcome, Barry.
Hello, thank you, thank you, thank you, thank you. Thank you for having me.
Oh, absolutely. Our pleasure. And the topic that Barry mentioned is absolutely exciting. That will be the first time at Verbose Mode that we're talking about quantum computing.
In Java.
Especially in Java,
Yes,
quantum computing
yes.
in general,
Right.
and in Java in particular. Now, what I know about quantum computing is that it's something from science fiction
Okay.
that is very good for AI.
It's potentially good for
Potentially
AI.
good for AI, and now it's basically does not exist.
Right.
Okay.
It's to say that it doesn't exist is not quite true. There are tests going on in various parts of the world, China and Europe in particular, and Korea and other places, where something called quantum key distribution is being rolled out. And quantum key distribution, hey, look, you and I want to exchange a secret, right?
Yes.
We have to have an encryption key,
Yes.
a secret key. I have to have a little secret formula, a code word that I use to encrypt my data. And you need to have that code word too.
In order to
decrypt it,
of course.
right?
Yes.
How do I pass that code word to you?
And that's the biggest problem.
That's the
because
biggest problem.
Everywhere we can intercept this code, suddenly this encryption is worthless.
With quantum key distribution, we can magically make it so that I have the code and you have the code, and we don't transmit it between one another to have a common code.
Okay, that does sound like magic.
It is. I think of it as magic.
Okay.
Most of the things in the quantum world are magic, and that's why I love it.
Okay.
Yeah.
Oh.
Now, the other thing is, if we get to have large enough quantum computers, the bad news is they'll be able to crack RSI in minutes and other things.
Yeah,
So,
and then it will be a very good cause to upgrade to quantum encryption.
And there are other styles of encryption called post-quantum encryption that are being researched and developed in order to make it so that these advanced quantum computers can't break those other modes, those other schemes.
I think Tux here is going to have a very good business once that happens.
Yep,
Because
yep.
we are about upgrading libraries, and there will be a lot of upgrades, a lot of security patches to do in the libraries.
There's already in Java 25 post-quantum encryption APIs.
Oh wow! Okay, before we jump to Java and quantum computing. So I understand the part about, well, I don't understand the part about the key distribution. But theoretically, I think understand what it will achieve.
Right.
Now, this is not the only usage. Obviously, what I hear a lot is quantum computing in the context of AI.
Well, it should work well in the context of AI. The jury is still out. To do real quantum computing, to solve problems, not quantum computing to distribute keys, but quantum computing to crack RSA,
or to generally do
computation,
computation.
takes a quantum computer with thousands and thousands of so-called qubits. A qubit is a quantum bit.
And now we have a computer that has one?
We have computers that have 100.
100.
Depending on who you ask.
Yeah, okay.
100, a few more 100. The ones that I played with, a handful of qubits.
Okay.
Okay.
All right. Now, this sounds...
Because I don't have the money to play with the bigger ones.
This sounds a lot like Moore's law and this kind of stuff. It's just like a linear or non-linear progression from smaller computational resources to larger
Exactly,
computational
and the
resources.
engineering problems to get machines with larger computers are being worked on constantly.
Exactly.
Every minute.
Of course.
Now, when will we have quantum computers that can actually solve real-world problems? Depends again on who you ask. I've heard 2031, maybe. I've also heard
That's very soon.
2030. Yeah, well. What's happening now, you see, is our data is being stored as it's being transmitted.
Yeah.
And they can't decrypt it yet, but they're keeping it. They're harvesting it now so that when they have quantum computers, they can finally...
So someone is already starting preparing to the day that they will crack all the encryption
If there's
very
something
easily.
malicious to be done, somebody is doing it.
Absolutely.
Yeah.
Yeah, but this is still about the encryption, and I understand how critical that is.
There is a link,
Yeah.
right, between quantum and AI.
Okay,
Right?
yeah, that's like...
But it's much, much less mature than the solutions to these other problems. There is theory that with quantum we can do better with AI.
Right.
But I'm not going to go ahead and say, oh yeah, that's right around the corner. It's still a very much in alpha field.
So
part.
the most practical usage that you see is encryption.
That's one of the more practical usages. There's another way of doing quantum computing where optimization is very much alive and well. And in fact, there have been some pretty good announcements about what they can do with optimization problems. So the idea is, imagine a bunch of stuff, quantum stuff.
Magic.
What?
Magic.
Nope. Quantum stuff.
Stuff, not
right?
magic. Definitely, absolutely different technical term. I'm sorry for the confusion. Stuff is definitely something different.
I love the confusion.
Yeah,
That's one of the things that's appealing to me. Imagine a ball of stuff that's
Okay.
quantum-like, right? And it's hot.
Love it. I love the technical
Absolutely,
the
absolutely. This is very,
ball
very
of
precise.
stuff.
A ball of hot stuff,
of
right?
hot stuff. Excellent.
And the hot stuff is somehow mapped conceptually to a problem state in which things aren't optimal. Oh boy, what does that mean? What's the best?
Blanks
Wait,
there.
whoa, I can do it. What's the best mix of oils, crude oils, that you can mix together in order to make the right amount of profit from that combination of crude oils? What's the best allocation of your resources so that you can optimize the benefit that you get from those resources? These are optimization problems. The classical one is, how can you travel from one city to another in a round trip and not visit any city more than once and do it in the quickest amount with the least amount of travel?
Okay, how did it?
Okay, so you take that and you somehow mirror it in this big hot ball of stuff. The structure of the hot ball of stuff is somehow has the same structure as the optimization problem.
Yep.
Right?
Yep.
Let the hot ball of stuff cool down. When it cools down, then what you've got is a damn near good, damn near optimal solution to the original problem that you said, that you started with. Okay? Now, if it sounds vague how you take a problem about traveling
the optimization
and map it
problem.
to a hot ball of stuff,
Yeah.
well, that's something that if I wanted to explain it, I'd have to start drawing with my hands, and that wouldn't be very effective. So I don't think I'll do that.
Yeah, absolutely.
The point is that you can reduce one problem, one kind of problem, to another kind of problem. And the classical way that I explain that, thanks to one of my students, is with the movie The Karate Kid.
That's a great movie.
How do you learn how to defend yourself against a punch?
You polish a car.
Exactly. You turn one problem into a completely different problem, right? So how do you find out what's the best way to travel around, minimizing the amount of flights that you make? How do you find out what's the best way to combine resources in order to optimize the amount of benefit that you get from those resources.
Yep,
You
yep.
turn it into a completely different problem, hot ball of stuff.
I love it. I love it. I love it. Now we have a couple of minutes left. Let me ask you something very interesting about Java.
Okay.
Now, usually Java spec is way behind the hottest trends. Think about how long it took for Java to adapt to cloud or to cloud native containerization and this kind of stuff. Once it's already been all the rage, Java kind of community process caught up and came up with some JSRs and stuff. What I hear from you is that here suddenly Java is on the bleeding edge. We don't even have the quantum stuff.
That's actually not true. There are several languages that you can use to program quantum computers. Now, what you're normally doing there is you're programming a classical computer to control a quantum computer. So what you need is a language that says, okay, I want this qubit to do this, and I want that qubit to do that, and I want some other qubit to interact with this qubit in a certain way. Okay, let's write a basic API SDK, and IBM wrote theirs. They call it Qiskit. It's written in Python. Right? There are others. Microsoft has one that's written in C#. Right? Okay. Johann Voss has graciously given me permission to talk at conferences about like this about his API called Strange. And is it used everywhere? Is it cutting edge? Well, no, but it's great to be able to do Java and to be able to do quantum computing in Java.
This is what I mean. This is what I mean.
Yeah.
This is something that not every programming language has, and Java has it, and this is great. And we as Java developers can start playing with it and you know, being out there somewhere where not a lot of people are.
It's great fun. Let me tell you, when you start imagining what's going on in the quantum world, it's mesmerizing.
Nice.
It's beautiful.
Yeah. Barry, thank you very much. That was very, very interesting, absolutely unusual for our, for me, for our audience, for this channel. That was a delight. Thank you very much.
And thank you.
And you all stay tuned for more episode of Verbose Mode by TaxCare Dev to Next. Tomorrow we start in the morning, and you will get notification in all our channels such as LinkedIn and Twitch and X, and then keep following us on our YouTube channel, and we'll see you tomorrow. Barry, thank you.